All right, how's it going, everybody? I'm going to teach you how to memorize the 20 amino acids, the names, the structures, and some other things about them too, all right? So we're going to dive right into it here with the nonpolar amino acids, okay? So there's 7 of these, and a couple of things before we get into this, okay? They're nonpolar, they're hydrophobic. Well, why are they hydrophobic? It's because they are full of hydrocarbons, okay? And these are the 3 that you want to familiarize yourself with. You're going to see these carbon-hydrogen bonds everywhere, okay? Anytime the carbon is at the end, it's going to have H3. Why? Because carbon likes to have 4 bonds, right? So it's going to have a bond each to the hydrogen, and then that 4th bond. CH2 is always going to be in the middle like this, and CH is going to be at like a triple junction like that, okay? And if you remember electronegativity, barbecue chicken nuggets only fried, F4, like alt F4, is your electronegative, and these all go back, remember, by a half. Okay, and then hydrogen, if you will remember, has an electronegative number of 2.1. So with all of these CHs, the difference between 2.1 and 2.5 is only 0.4. So 0.5 is the cutoff really for a polar molecule. So that's why hydrocarbons are nonpolar, and that's why these are hydrophobic, okay? All right, so with that said, the mnemonic you want to memorize here is glaciers always vaporize pros, like professionals. Let me in. If you're a fan of this Eric Andre gif, then you will know all about let me in, okay? All right, and these are in a specific order, and I'm going to tell you that in a second, but let's name them first, okay? So we have glycine, everybody's favorite since it's so simple, alanine, valine, proline, and then this little triplet down here. We have leucine, methionine, and isoleucine. Okay. The other thing I'm going to have you remember, and you can get rid of this eventually, but to really help you memorize these, is just a code that goes with this. I put them in this order. You might not have seen them in this order before because they're in order of complexity. And this is basically how many pieces or how many parts they have. So if you can remember 1, 1, 3, 3, 4, 4, 5, this is basically everything you need to draw all of these, okay? Before we dive into it, though, let's look at a couple of things we want to remember about some of these, okay? So valine, we can remember, is shaped like a V. Proline is like the boss fight of this first group of 4 because it's a little complicated. But proline, you want to remember, has an NH2 plus in it. Proline also starts with the letter P, which makes me think of pentagon, because it's going to have a pentagon. Then I also think of pros. When a pro wins a medal, they stand up on a podium that kind of looks like that, okay? Leucine and isoleucine, of course, are linked because they are isomers, so we'll keep that in mind. And then methionine, I think of 2 things here. It's the second to last in my list. And methane smells kind of like sulfur, right? So I'm just going to remember sulfur here. Okay. All right, so we can dive right in. So just remember that all amino acids are going to start with a carbon, have a carboxyl group, a hydrogen, and an NH3 plus, okay? It might be written with the hydrogen on the right and the carboxyl up top also. It's not super important for this part, but just, all right, so keep that in mind. So anytime I draw one, we're just going to assume that this part is here, okay? So we'll go ahead and start with glycine. So glycine just has one part. It's the simplest of all of them, and it's just going to have a hydrogen. So that's glycine, okay? The simplest. All right, moving on to alanine. Alanine is just going to introduce us to a hydrocarbon, okay? And it only has one piece, which is going to be carbon. And we just learned that at the end of a chain, a carbon is going to be a CH3, which is called a methyl group, okay? Valine, which we know from our code has 3 parts to it, is just going to be 3 carbons in a V formation, right? So 1, 2, 3. You see that upside down V? Now, using what we learned up here, we can fill in our hydrogens, or you can just remember that carbon likes to have 4 bonds. So these have to be CH3s because they're at the end. This carbon in the center already has 3 bonds, so it's just going to have 1 H, right? It's just going to be CH. That's valine. All right, proline, like I said, is the boss battle of this first group because it's complicated. It's actually super fun to draw, though, okay? I am going to draw the upper part of this one, too, and you just have to remember we're going to start with carbon, right? And with proline, carbon has gotten itself into this mess, and it's kind of in a cross here, okay? So it's still going to have its carboxyl group. It's going to have its hydrogen, but it's going to have an NH2+, okay? And then, remember, proline and pentagon. So the carbon is going to be at the top of this pentagon, and we're just going to have to draw the rest of it. So what do we fill the rest of it in with? Well, we just filled in with carbons, okay? And remember that proline, using our code, has 3 parts, so we just put in 3 carbons. You do have to remember just to make that NH2, to make that change, okay? But technically, the only parts of proline is this podium that we drew before, right? With the pro that's going to stand on top. And we can't forget our hydrogen. So this is a C that's already bonded, so they're actually just going to be CH2s all around, all right? That is going to be our proline. So complicated, but it's kind of fun to draw, okay? All right, so that is our first 4 that you've drawn already. So now we're going to go to this next group, the let me in, the leucine, methionine, isoleucine, okay? So let's go to leucine. And what do we know about leucine? It has 4 parts, and it's going to be related to valine. It's basically just going to be valine branched out 1 more, okay? So it's going to have 1, 2, 3, 4 total carbons, and then we'll put in our hydrogens. That will be CH2. This will be CH. These will be CH3. Okay, so that is leucine. All right. Now, even though methionine technically is next in terms of how many parts, because it has 4, we're going to do isoleucine next, because I'm going to teach you the relationship between these, and you'll never forget it. Okay, the only thing you're going to do here is with leucine, CH and CH2 were like, let's trade. We're going to trade positions, and we're each going to take a CH3. And that's all you have to do. So CH is going to come up here. Where that 4 becomes 5, however, and this is how the book likes to draw this, is that the C and H that comes up is going to split itself. Okay, and remember in the deal, it got a CH3. CH2 is going to chill down here, and he gets a CH3 also. Okay, so you can just look and see the CH2 that was here is now down here, and that both CH3s are still in there too. All right, and total 1, 2, 3, 4, 5 pieces for isoleucine. Okay, all right, the last one we're going to draw is methionine. Methionine. And what did we write when we wrote this, right? It's second to last. It has a sulfur in it, and it's got 4 pieces. This is simply a line of carbons with a sulfur second to last. And there's 4. So 1, 2, sulfur, 4. And then you just load up your carbons in the center. CH2s, sulfur's just by itself there, and that's going to be a CH3. That is methionine, okay? So these are your nonpolar, aliphatic, hydrophobic amino acids. All right, moving right on to the next ones. This is our polar hydrophilic amino acids. All right, the mnemonic we're going to remember here is school children play tag, okay? And we will name them here. And again, they're in a specific order, but this is serine. This is cysteine. Immediately, when I hear cysteine, I think Sistine Chapel. And when people make noise in the Sistine Chapel, you tell them shh so they can be quiet. All right, this is threonine. Threonine. This is asparagine. And this is glutamine. All right. We're also going to include in this one our negatively charged acids, okay, which are going to be aspartate. So these are kind of an add-on here, and glutamate, just because they're so closely related to asparagine and glutamine. Okay. All right. Now, a couple of things here. So we do have a code for this one too. If you'll remember, the nonpolars were 1, 1, 3, 3, 4, 4, 5. So if you remember that 4, 4, 5 already, and we are going to separate these. That 4, 4, 5 comes here too. 4, 4, 5. And this is our second round. The amino acids we're looking at, so these are going to be 2 and 2, okay? I also have an 8.2 here. This is the pKa value of cysteine, which we're going to have to remember, so I will include that there, okay? Also, 3.7 and 4.3 for aspartate and glutamate are values we need too. Okay, so what do we need to know about these? So remember, polarity, if we think about electronegativity again, we are introducing a hydroxyl group to this. And if we look at barbecue chicken nuggets, only fried, 4.0. If you look at electronegative oxygen with a 3.5 and a hydrogen, which is 2.1, that 1.4 difference is plenty to make a very polar bond, right? So that's why these are going to be polar hydrophilic, okay? All right, so what else do we need to know here? When I look at threonine, which I remember is like the highway 309, it starts with the letter T. Remember, the letter T has 4 junctions like this. That's going to come into mind, okay? This is where we start to get some of the madness with remembering 3 letters and 1 letter, and I'm going to tell you what I use. So there are a couple of things here. I like to show The Walking Dead. There's an Asian character named Glenn in the show. So I remember Glenn is Asian. I also remember that, I can even draw him. There's Glenn, that he likes to eat ice cream cones. All right, but they're spelled a little bit different. Cones that are spelled like that, okay? I also think of that asparagus. Oh, geez. Bluetooth issues. Asparagus is nasty. And I think of glutamine as cutamine. Okay, all right, so why? Why do you need to remember any of that? Well, because asparagus being nasty, that's where your letter N is going to come into play. Glutamine being cutamine, that's where Q is going to come into play. Okay, Glenn come on, Glen is going to be here, and Asian, ASN, is going to go, oh, I'm sorry, I had those switched. Asian and Glen go there. So that's how you'll remember the letters for asparagine and for glutamine, okay? Might as well go right into, we'll keep the cone up there. Might as well go right into the letters for the acids here. So these are lucky. These just get what they start with. So asp and glue. And this one's easy because glue, if you keep writing the word, you're gonna get an E anyway. But I also think of like acid the drug. What do you need? You need drug enforcement. So DE are going to be your letters there. Okay. All right. So now that we have all this set up, we can actually start drawing some of this. So just remember that hydroxyl group we were talking about, because serine, really all serine is going to do is introduce us to that. So I'm going to start serine up here. Serine is going to start with a carbon because she has 2 parts, and then she's just going to say, hey, welcome to the polar show. This is my hydroxyl group, right? And remember, a CH that goes in the middle here is going to be a CH2. Okay. Now we can go to cysteine. Cysteine's a little bit of an outlier, but she's the same as serine, but she is going to introduce a sulfhydryl group, that SH, okay? I think I erased it by accident, but remember, when we're in the Sistine Chapel and people make noise, what do we say? We say shh. So that's how you can remember that. So cysteine is just going to have a carbon and then an SH. The carbon's in the middle, so that's going to be a CH2 also, okay? All right, so now threonine, kind of our boss battle of this one, a little bit more involved, but not really, okay? So if you remember that a letter T having 3 junctions, we're going to have 3 parts to this. Or I'm sorry, letter T has 4 junctions. We'll have 4 parts to this. In the center is going to be a carbon, okay? Just another carbon under that, which will end like this. And then, like I said, 309, like 309. After the 3 here, I remember O. We're going to reintroduce that hydroxyl group again. And then we're just going to put another H here. So I kind of remember, like, if you look at the letter H, it has 3 lines. 1, 2, 3, okay? And there's 3 total hydrogens that you're drawing the actual H for. So you literally have 3 O and then 9 with 3 lines in each H. So I don't know, a little far-fetched, but I kind of keep that in mind to kind of remember when I'm drawing this one. And that is 309, okay? All right, so now we have asparagine and we have glutamine. So why did I have you think of that ice cream cone of Glen holding the ice cream cone? Because, and remember, this has 4 pieces, okay? So asparagine is just going to have a carbon, and then it's going to have this ice cream cone part. It's going to have a double bond to an oxygen, and it's going to have an NH2 at the bottom here. So that's where that COHN comes into play. And then remember, this is a CH2 because it's in the center there. That's asparagine, okay? Glutamine, asparagine's big sister. If you remember our code, glutamine has 5 pieces. So all she is going to do is add an additional carbon before her cone. CONH2. No charge or anything on the NH2 there. And remember, this is a CH2 and a CH2. Okay. So that is glutamine. That is asparagine. Okay. Last two parts of this are aspartate and glutamate. Now, a carboxyl group, right? Carboxyl group, which is like vinegar, like acid, right? Acidic acid. Adding this carboxyl group is going to make something acidic. All you're going to do is, the fun is over, you will remove your cones on both of these and just replace it with a carboxyl group for both of those. That makes glutamine, glutamate, and that makes asparagine, aspartate. That's it. That's all that happens there. Everything else stays the same in the amino acid, but the COO minus comes in. That's where your negative charge comes in. That's why these are the negatively charged acids, okay? Because your amino acid already is neutral. Now you're adding in a negative charge. That's where that comes into play, okay? All right, so that is our polar hydrophilic. Okay, and we're moving on. So now we are at the aromatics, and I think of aromatic as this nice little carbon flower, right? Smelling nice, like an aroma. And these, the mnemonic I think of here is Phil tied the race, and then he tripped, right? So Phil, of course, is going to be phenylalanine. Phil of the future, starts with an F, all right. He tied the race, tyrosine. When I think of tyrosine, I'm going to misspell it intentionally. I really think of tyrosine, right? And that's going to be Y. And then tryptophan. But when you trip in a race, what happens? You don't get the W. All right, so those are your three letters for that one. Okay, at this point, you probably need a drink. You have to wait for when you're 21. You have to wait for when you're 21 to drink. That's going to be our code here, okay? Anything else we need to think about this? Tyrosine is going to have a pKa value that we need to know. That is going to be 10.5. Phenylalanine is going to have some nonpolar characteristics because of the hydrocarbon that is in it. And tyrosine is going to have polar characteristics because of the hydroxyl group that is in that. Okay. Really, the name of the game of the aromatics is, of course, that carbon chain, that carbon ring. Okay. Phenylalanine, which I'll just put as PHE. All it's going to do is start with a carbon, like many do, and then it's just going to have that beautiful pentagon, or hexagon. Of course, this will be a CH2, and that's it. That's phenylalanine. Nice and simple, and that has one piece. Tyrosine, which again, tyrosine, you will never forget that, is going to start off the same exact way. And you'll have your nice pentagon. But remember that polar part of it, it's just going to add a hydroxyl group here, okay? And it fits because it has two pieces, okay? Tryptophan absolutely sucks, all right? Tryptophan is your boss battle here and is very complicated. I'm going to see if I can draw it from memory. Tryptophan, this guy. Okay, what he's going to do is he's going to knock this wheel that we have so nicely in phenylalanine and tyrosine, and he's going to knock it on its side. All right, still going to be a hexagon, but he's going to put it on its side. And he's going to build a house on top of it, okay? And where's he going to build a house? He's going to build it in New Hampshire. All right, he's going to build a house, which is shaped like a pentagon, and he's going to build it in New Hampshire. Okay. Now we need 4 pieces of tryptophan. Now, the bonds here, we are going to have a double bond here, double bond here, there, and there. Okay. I believe this is a C. I'm going to have a carbon here. I have to cheat because I did not remember this one. And a CH2 here. Okay, so those are the 4, even though, there's more carbon atoms in here, these are the 4 pieces that we need. But I try to just remember that the wheel is knocked onto its side. You're building a pentagon on top of it. It's in New Hampshire, which is why you have this NH here. And then you kind of just load up with carbons. The CH2 is the same around all 3, so that one might take a little bit of time to memorize, but there you have it, okay? All right, now moving on to the final fight here, our positively charged amino acids. And these ones are tough, okay? These ones I like to call the last heckin' aminos, because it's the last group, right? And of course, we're talking about none other than lysine, histidine, and arginine. Okay. What happens? Lysine, Lysol. What happens if you don't have Lysol to kill germs? You get killed. Arginine. And histidine is boring, and it's just H. All right. 3 pKa values that we're going to have to remember here. There's also a code. All right. At this point, you just want to sing because you're almost done. And how do you start a song? 5, 6, 7. And that's going to be this. All right. Okay. That's kind of a good starting point because just histidine 6, it matches its pKa value. Arginine is double histidine at about 12.5. Lysine is about double its number here, 10.5. I don't know. Take it for what it's worth there. Okay. So, lysine comes in and is like, hey, you remember that initial amino acid structure that looks like this? Right, that's where we started. Let's bring that NH3 back, and let's put it down here. And we'll keep the plus on. And let's just put carbons in the center. Let's load it with carbons. How many carbons? Well, we have 5 pieces in this, and we already have 1, so we're going to put 4 carbons. 1, 2, 3. Never make enough space for this one. 4, and 5, our 5th piece. That's it. It's just 4 carbons, and they're all already have 2 bonds, so it's going to be CH2s all across the board. That's lysine. Done. Okay? And that's where your positive charge comes in, because remember, these are going to neutralize themselves. This is where this positive charge comes through, okay? Now, to get from lysine to arginine, we are going to skip histidine. Histidine is hell. It goes down in history as the toughest to draw. So we are going to go to arginine, okay? And to get from lysine to arginine, here's what happens. This NH3, this amino group down here, it explodes. Not for real, but in this video it does. It explodes, and it knocks out that CH2, okay? And when the explosion is over, our trusty friend carbon is surrounded by a bunch of NHs, all right? So let's draw it. We're not going to draw this part. We don't need this part anymore. But we're going to have those 3 CH2s. Okay, and then we're going to hit it with an NH. Carbon. An NH down here. And after this explosion, carbon really needs something strong to hold on to, like another NH. And I think the way this goes is that I think it's this. Probably wrong though. Yeah, I swapped the plus. The plus is going to go here. Okay. Which actually makes sense, because if you look at nitrogen with 4 bonds, 2 H's, and a double bond, 5, 4, 3, 2, 1, that's going to give us the +1. So you can double check yourself to know where the charge goes. Okay, that is arginine, all right? And it has 7 pieces, 1, 2, 3, 4, 5, 6, 7, and that's it. Okay, histidine is the toughest amino acid to draw of all of them, all right? This is histidine. It's the final boss, all right? But here's the trick for histidine. You already tortured yourself with tryptophan, remember? Histidine is actually kind of similar to tryptophan. Okay, so what happens here is that histidine comes in. Come on, we're almost done. Histidine comes in and basically says, we're knocking this wheel off completely. We don't need this ring. This is an aromatic, all right? And we are moving this house, and we're not going to be in New Hampshire anymore, okay? So what the hell does that mean? Well, the CH2 is going to remain here. And that same pentagon, with a carbon being there, that same pentagon is going to be here. And we just kind of have to fill it in, all right? This will be a CH. It's not in New Hampshire anymore. New Hampshire is going to move here. We're going to bring the hydrocarbon back in. We're going to throw a nitrogen here. And we're going to shift our double bond like this, okay? So that is histidine, CH2, CH, CH. That's histidine, all right? So if you look at tryptophan, you can kind of base it off of that. But that is all 20 of them. All right, so hopefully that was helpful. Hopefully I didn't forget anything. But that's it. Good luck and have fun.